We have a big treat here. I know we've all been waiting for it. I know I have. I have the distinct honor of introducing our next speaker, who is a friend and colleague and has been an inspiration my whole life, I want to say. He is a big reason that I got to Berkeley, so I am indebted to him. And I think probably everyone would agree. I think he should be, we could call him the whiz kid of Oz. John Canny did his undergraduate degree at the University of Adelaide in Australia, and in computer science, theoretical physics. Then he went to MIT, and he worked with Bertolt Horn and developed something called the Canny Edce Detector. This has been cited 10,000 plus times, still in use all over the world. And then John did an amazing pivot, and he decided to move away from computer vision, even though he was this rock star, and move into motion planning. And then he started working with Tomas, who's here, as his advisor, and he tackled the piano movers problem. Now again, this has been addressed by Schwartz and Scharir, two of the great mathematicians of our time, and you know, it was the kind of thing where most people would be intimidated, but not John. He waded into there and actually made a huge contribution by lowering the complexity from doubly exponential to single exponential, by combining ideas from a number of different areas, from stratifications to multivariate resolutions, developed a gap theorem, put this all together to basically develop what was now known as the roadmap algorithm. Then, and he won the ACM dissertation award for that. And then he went on to come to Berkeley, and has been advising a great group of students and collaborating on projects ever since then. He worked on vibratory plates, something called the universal planar manipulator. He developed the Canny, Ferrari Canny grasp metric that we talked about today. Lydia mentioned him many times, as you saw his name cited in the history of motion planning. He did the fast collision checking also, Dinesh and Ming. He proved a number of p-space hardness results. He did RISC, reduced intricacy in sensing and control back in the day, and then worked on Prope, something called Personal Roving Presences, which was an early, what he called space browser. These were robots that could be controlled over the web. Then he did another pivot. He started getting very interested in human-computer interaction. And then he's done a huge amount there. He's become a leader of that field, and he's done work on collaborative filtering with privacy. He's developed something called the multi-view teleconferencing system. He's done work on like auditory analysis from cell phones in India, computer-aided learning. He's consulted at Yahoo, eBay, Google, and now is doing big data and machine learning. So he is the whiz kid of Oz. Please welcome John Canny.
Hi, it's fun to be back at Wafer after a bit of a break. And I would really thank Ken for the invitation. Also thank Ken, Nancy, Lydia, and many others who have kept Wafer going for this period. It's a pretty impressive corpus that's been put together over that time. So Ken asked me to give a retrospective on the work that I've done. So it's presumably supposed to be full of jokes and deep insights. I tried. I just hope they're clear which one is which. If not, I'm going to drop some. I'm going to drop some hints just in case. So this is just to set expectations realistically. This is going to be a Cook's tour. Thomas Cook in the 1850s invented the group tour and took Englishmen and Englishwomen around the world in ships and buses and went to famous, amazing places, took these big group selfies and then put them on the bus again and went somewhere else. That's the character of the talk I'm going to give. So let's start with computer vision. So that was my first domain at MIT. I worked on the Canny Edce Detector, which is an edge operator. I'll give you a bit of context in a minute. Just this photo is a really nice photo that Joe Fish K took when I was at Yahoo. And it shows me as the edge detector. So you might see in the image there, there's a picture of you two and there's the edge. So I'm also an edge detector. All right, so to give you a bit of context, when I started at MIT, it was very much in the shadow of David Marr, a great researcher who started this computational perspective on computer vision that was very influential and really kind of formalized a discipline that had had perhaps a little bit too much entropy and created this notion of a hierarchical representations for vision, going from input images to edges, and then volumetric and spatial descriptions. So anyway, basically starting with edges. So edges were clearly important in that framework. And I worked with Berthold Horn. I also kind of drifted over to Mike Brady fairly early too. And Mike's suggestion was to look at some of these edge detectors. And there were quite a lot of edge detectors, and most of them were optimal, which is kind of strange. Even the optimal ones often weren't very good if you use them. On the other hand, there were some that worked well that had more, that was actually work with David Marr, that was biologically inspired. And David's work, by the way, wasn't just literally biology measuring cells. It was actually using psychophysics to try to get at perhaps more higher level, more functional aspects of human behavior. So the question is, what's going on? And I think after a while, the insight was that, well, the problem is people haven't really defined the problem they're trying to solve properly. It's got something to do with detection, something to do with localization. But the methods generally were sort of assuming a solution or a family of functions before they'd really started solving the problem. So the approach I took was to use variational calculus, which allows you to optimize over a full function. In this case, it was a detector function, or the detector impulse response, basically. So that gives you arguably a fully, you're really spanning the set of solutions that way. And then the performance criteria become functionals on that function. And yeah, basically, you typically want to optimize signal-noise ratio. But when you try to do that, is often when you try to optimize for one thing, you actually break other performance criteria. And so designing an optimal filter became a sort of more of an iterative process. First of all, the optimal detector really is just another, if you're detecting step edges, the optimal step detector is another step, but it has terrible localization, multiple responses. Actually, not multiple responses, but if you instead try to optimize for localization, you get something else that has multiple responses. There's a trade-off, and eventually, after solving the problem numerically, you get something that looks like the top curve, which you can approximate with a Gaussian. And there are some other important kind of execution details in the algorithm that have to do with really making it work on real data. And again, you sort of try it on some images, look at the images. If you just try a simple filter, I'm having more and more trouble seeing the pointer. But if you just try a simple filter, you notice it breaks the edges up. So you can add hysteresis, you can thin the edges, and you get pretty good results. Yeah, so it's widely available in different languages. C++, MATLAB, and ActionScript. Okay, so some takeaways from that. This is not a joke. Research is like a game with nature. It's important to figure out, first of all, the objective of the game that you're playing. Make sure you don't get trapped into an incorrect interpretation of what you're trying to really do. And then to figure out what options you have. A lot of research is over-constrained in that people assume a solution like somebody else's solution. The first step really is to figure out what your design space really looks like. All right, so on to roadmaps. So let's see. Okay. So yeah, so around about 1983, there was a very interesting result that a few people have mentioned, I think, already. The Schwartz-Sharia paper on using cylindrical algebraic decomposition to basically break up configuration spaces into cells. From the adjacencies of the cells, you can figure out the connectivity of the entire space. And yeah, so then you can plan paths through sequences of adjacent cells. And beautiful algorithm, both the algebra and the geometry work all the way through, but it had this excessive complexity, which is a bit disturbing. So double exponential. In theory, it should only be single exponential based on comparison with any other kind of geometric problem. Yeah, and the lower bound's only single exponential as well. So the work I spent a lot of time on my thesis was matching the lower bounds. I guess I'll go quickly through this since it seems like a lot of people still know what this is. So the basic idea is to construct silhouette curves. You can think of those as the pre-images of a projection map. There we go. Around the edges, those are kind of across cross sections. They connect different sections, fixing the x1 coordinate of the object. Within each region, you have a finite number of of the silhouette points. And if you can, in addition, connect those up, then you'll have a fully connected map within each connected component of the object. And of course, you have to jump on and off, which you use the same method of slicing in the planes where the start and end points are. Okay, so so that's the geometry, which is pretty easy to explain. The algebra is not so easy to explain, but that actually worked. And so that was a fairly big result compared to the recent work before that on motion planning. And so it ran the dissertation award and also a Fox, which is a MACTI award, which is the student award at Fox. So somehow roadmaps got a bad rap of being really difficult to implement. I'm not sure why. We implemented several of them. Basically, those are the worst case bounds that I just showed you. You don't have to enumerate all of the critical points. We did several versions, one of them for non-holonomic planning, three-dimensional configuration space. With Ming Lin, we did kind of Voronoi roadmaps, basically adding one dimension, which measures the height or distance, the height of which measures the distance from the obstacles. Constructing a roadmap by projecting using the height will give you maximum clearance curves. And you get these bridge points. And in practice for environments like that, even in configuration space, there's less than about a dozen critical points, so it's not so bad. They have lots of constraints. You can enumerate them in practice. And Brian Mertic did also a Voronoi roadmap planner that combined non-holonomic constraints. It tried to find maximum clearance paths first that then allowed you to maximally maneuver and get around the path even with non-holonomic constraints. And so, let's see. So in roadmap evolution, there was our original work, and then there was a big step or innovation with probabilistic roadmaps that didn't try to do the algebra or the sort of Morse theory, just enumerated sample points, made it very simple and fast. Howie's work, which is a bit more like the original roadmap work that uses sensors to incrementally create roadmaps. Steve Laval worked on Pareto. I think everybody knows this work. Pareto optimality early, and then also on tree-based maps. And finally, Nancy's work on both the PRMs and also the protein folding. And I guess maybe less well known in this community, actually I didn't know about any of this either. Apparently there have been many years of work trying to improve the original algebraic bounds, which were originally, although they're single exponential, you'd see do to the O of n squared, which is really quite a bit worse than the lower bound. And so one of Jean-Charles Fauger's group, his robotics group in France, recently improved the algebraic dependence down to really single exponential. And there's also been some work on generating more or less the original style of roadmap curves numerically, and that runs now in 4 and 5D as a system called Neuroa. So that it does seem to be still working. So in the takeaway from that work really was simplifying. If you're trying to describe the topology of a complicated set, the minimal description of topology is just curves or one-dimensional approximation, and it's sufficient for motion planning. So it's always a good step to figure out the simplest object that you can create that solves your problem. All right, so let's see. So from that work, though doing numerical roadmaps and trying to deal with more complex environments suggested more local incremental approaches to the problem. So specifically, and I think Lydia mentioned this earlier, collision detection was a critical step in doing that. So, so we worked first on incremental distance calculation. So that was Ming Lin's work early on. And the idea is very simple to present. So This is just 2B, but I'm sure you'll get the idea if you don't already have it, which is you basically track a pair of closest points. As one object moves around, the pair moves and it switches from feature to feature only occasionally. But so if you already know the feature, you can verify that if they're the same, you can verify that in constant time. But also if you switch from one feature to an adjacent feature, if you pre-compute the Voronoi regions before you run this algorithm, you can also in constant time do the update. So, it's still a reasonable algorithm. There was Ming and Dinesh's work later on iCollide, and there's even an update on that called Swift. And then Brian Mertich, as part of this simulation work, developed VClip, which is still a fairly, I think all of these are still fairly competitive algorithms. Let's see. So here's an animation of Lin Canny, in case it wasn't clear enough. I think it probably was. But you can see the closest points moving around. The objects aren't convex, but the algorithm's running between pairs of connected objects. And so works quite fast and will allow you to compute the closest point pair and do Voronoi, evolution along Voronoi curves as well. So let's see. So I guess, so takeaway from that work was you look for the easy part of the problem. In this case, rather than collision detection starting from no knowledge, you just look at closest point tracking. So the incremental version of the problem is really a lot easier than the cold start version. So that's what we did. And we moved, because I guess there was an interest growing in dynamics and robotics, we moved fairly quickly into dynamic simulation. And I'll point out, happy to point out that this paper on impulse-based and dynamic simulation, the paper of Brian was in the first wafer in 1994, which was in Stanford. And basically, well, the challenge we're trying to address is that in complex real-world dynamics, objects change state a lot. If you have multiple contexts, if you have grippers or pegs in holes and so on, some of those states can be indeterminate. It's not really clear. There are multiple possible solutions for the forces, and they kind of depend on history to really figure out what happened. And the full version of this probably requires finite element simulation of deformation. So, but the basic two extremes. One extreme is to do kind of microscopic simulation, do finite element modeling of deformation and contact, which is going to be accurate, but typically several orders of magnitude slower because you have both spatial resolution and very fine time resolution to do that successfully. The converse is to try to use constraints to macroscopically simulate the behavior of the system with forces. The trouble with that is it is generally fast, but it has a lot of trouble with either transitional cases, indeterminate cases, and a variety of other cases that we care about. So we explored a hybrid, which is essentially to abstract away from the sequence of events involving an object interpenetrating or colliding and then compressing the object and then being pushed out again, and friction being applied throughout that interval with a single event, which is an impulse. So it's kind of like a rebound type event, simplified but still valid in terms of the forces and the momenta of the body before and after. So there's definitely some tricks to get it to work, but Brian did a fantastic job of working through that and actually getting the method to work very well. So here's a couple of versions of the simulation. The one on the left is showing a rattleback top. That's a very simple shape. Basically, it's what you see, an ellipsoidal shape with an asymmetry in its mass. So you can probably just see on the green object there's a slight red dot. That's a small point mass that's been attached to it. And the effect of that mass is to cause the object to rattle for a while and actually change its rotational orientation. And the object on the right is the ball on platen example, which is a very surprising, correct solution to the problem of dropping a ball onto a record player, which nobody knows what that is anymore. But when those existed, they used to spin around. You could put objects on them. That's not what they're for, but you could put objects like steel balls on them, and surprisingly, the ball executes a circular strategy around some center, which is not the center of the record player. And you can see gradually the locus of that circle expands and even crosses over the center of the circle. And you can both do the experiment or do the much more complex physics, or you can just drop it into our simulator and it does the right thing. So these simulations show that even over long periods of time, the energy was correctly decaying slowly, the momentum was being correctly computed, and so on. So it works pretty well. And toward the end of the work, Brian added the ability to do open kinematic chains, propagate the impulses through that. And so these are old simulations, but still physically correct. And interestingly, I don't think much happened after Brian's work. He left and went to Merle. However, around 2006, it was picked up by the VR community, and Jan Benders did a lot of work on impulse-based simulation. If you're at SimPar right before this conference, you might have seen Owen Kuman's keynote. So he's developed Bullet, which is one of the main, or maybe the main open source physics-based simulator. And Bullet does several things, but one of them is impulse-based simulation, fairly close to what we did. And in fact, on the to-do list is adding vClip, because vClip was, for a long time, patented software from Brian's time at Merle. And fortunately, the patent has lapsed. So now it's hopefully going to make its way into Bullet physics. All right, so so move on from there. I guess I'm not sure the lessons there were similar to the other ones, so to keep things as simple as possible. So I struggled a bit to get some computer algebra in there, because I know I promised to do it in my abstract, so let's see how this goes. It is one of my favorite topics, but it's just not really easy to do in a very self-contained presentation, but let's try. So there's a beautiful theory, geometric theory of the solution of algebraic systems from kind of a subset of real algebraic geometry. And one of the key concepts is to exploit and model sparseness of polynomial systems. It's very important for people in robotics to know about this, because most of the systems we deal with are at least representable as polynomial systems, both the object shapes themselves, also the kinematics. We can use quaternions and so on. When you do it, however, the equations are typically very special. They're sparse, meaning not all of the possible terms occur. Like on this, so basically, the layout of these polytopes is the exponent vectors. So 1, the constant 1, has exponent 0, 0 in x and y, all right? And then x has exponent 1 in x and 0 in y. So we lay out the polynomial according to the positions of its exponents, okay? Some of you might have seen this before. These are Newton polytopes. They're both sparse because you're missing the x squared term here. On the one on the right, we're missing a lot of terms because that's actually has an xy squared term, so it's third degree. And when you leave out the terms, you actually force a certain number of the solutions to infinity, and you simplify and reduce the number of solutions you actually have to worry about. And especially with complex systems, you can actually get pretty dramatic reductions. Even though you're still roughly facing an exponential cost, you can still, especially in reasonable numbers of degrees of freedom, like 6 is an important number, you can often reduce the number of solutions to deal with by one or several orders of magnitude. So it's an important trick to know about. And well, basically what you'd like to do with this method is take the geometry and go as directly as possible to a method for solving the polynomial system. So the most direct way, and probably the best for a roboticist, the best way to do that is to convert from the original polynomial system to a matrix whose eigenvalues are the roots of the system. So I can't really go into all the detail. I have a paper going all the way back with Dinesh on that, but it's a standard reduction. Just wanted to focus on the geometry here. And basically, in the Minkowski sum you can think of as, I hope this is reasonably familiar, but the Minkowski sum for all of the polytopes, you can think of the Minkowski as being the sum of one of the polytopes with the Minkowski sum of the rest. And that second Minkowski sum gives you a whole set of exponents by which you can displace the first polytope. In other words, multiply your first polynomial by different monomials. That creates rows of a matrix, and if you do it just right, you'll get a solvable system. And it's, in some sense, it's minimal because you haven't done any reductions. You haven't allowed the system a chance to become dense, because it will very quickly if you try to do any kind of gas elimination on it. You basically have copies of the original polynomials in this very big matrix. It's big, but it's not much bigger than it has to be in order to have the right number of eigenvalues. So in a sense, it's the minimal way of solving the system, but it's still challenging to actually get this to work in terms of the counts matching up. So it's almost right. That picture is almost right. But unfortunately, if you actually do crunch through, it just doesn't work. There just isn't there's this mismatch between the set of polynomial shifts and what they should be and the degree of the matrix. So I kind of agonized and got very frustrated. And I did what every good roboticist does to a robot when you get frustrated, which is what? Kick it. Right. So, all right. So you kick it. What does that mean? Well, basically, you knock the points, the shifts off of the original grid, and then use the actual cell identities to figure out what rows of the matrix to create. And it turns out you can kick it any different way. Every time you kick it somewhere, it gives you a different matrix, sometimes even a different size matrix. All of them correctly give you the solution of the system, and you can actually prove that they do. Now, why they do is another story. But anyway, this gave us a nice result, which was an efficient algorithm for the sparse mix resultant, kind of arguably optimal way to solve very big systems. Near optimal matrix size preserves sparseness. You can solve systems with billions of roots. You can't find all of the roots, but you can find a few of them. Or you can solve smaller system, maybe a few thousand roots, actually very fast with eigenvalue methods, sparse eigenvalue methods. So yeah, so the takeaway, if it doesn't behave as expected, try kicking it. Doesn't just work for robots. I think we had an advantage working on this problem that we weren't algebraists who probably don't kick things as much, and if they do, they need a really good reason. We didn't need a reason. We just instinctively did it. So, all right, so telepresence. Yeah, so lots of interesting things were happening in the early mid-90s. Well, the web was happening. That was pretty interesting. But at the same time, it was also this virtual kind of very, if you ever looked at early mosaic screens, is also very sterile and divorced from the real world. And there were a few pretty interesting exceptions. Originally, there was the Trojan room coffee pot. At that time, it was very exciting. You could see how the coffee was going in Cambridge. And Ken's project, the Telegarden, which added this sort of persistence and actually nurturing and caring for some plants online with a robot in his lab. But anyway, it seemed for us an interesting thing to try. What if we could actually browse physical space, so have some kind of flying camera that you could move around in 3 dimensions. You know, maybe it would be more natural to do two dimensions, but like a real person. But at first we thought, well, why not do one more dimension? Then you could really have an experience that you couldn't otherwise have. So we built blimps, first of all. Back then, a few of you recall, we didn't really have digital cameras, and we had some basic wireless internet, but you couldn't fit it on these balloons. They carried about 1 pound. So we had a lot of analog stuff, analog control and camera data, and yeah, not much else. So it worked, though, and you controlled it from a mosaic panel. You had a separate video window, and you could talk to the people remotely. And yeah, here's a quick overview. Thanks to Eric, nicely curated video of this early Prope early space browser stuff. So that's cruising around our lab. Generally not a good idea to go outside. So they didn't, but it worked well enough for us to talk to people. You could cruise some interesting environments, like the T-Rex in our natural science building. We probably shouldn't have been doing that, but we didn't knock any bones off that I know about. But anyway, you got these unique perspectives of that dinosaur that you wouldn't normally get, and probably you can't get anymore. And yeah, we tried to make it so that it would actually servo at human height, so it could go around up and down stairs. All right, but there were some pretty big limitations that you would see if we showed you all of the real video, all of the uncurated video. But actually, a lot of the experiences that were the most interesting with the blimps were the human-human interactions mediated through the blimps. So we switched direction and started trying to design instead for that interaction, and that led to prop robots, personal roving presences, that could support a better, sort of more naturalistic set of nonverbal communication behaviors, like gaze, proxemics, which is just the position and orientation of human bodies, and spatialized gesture. And also that would support some of the situated spatial behaviors, like bumping into people, having informal meetings, and just people knowing that you're around. And also the body itself was a strong signifier, and that it caused people to pay attention to you, and it, in this case, initiated a lot of interaction. Okay, so we built a few versions of this. You can see they just basically, the main affordance was providing a camera and a video monitor. It might be a bit hard to see, but they had a monitor that would show the driver's face to people around it. And the later versions also had a pointer that you'll see in the video. So there was mobility gaze, video face of the pilot, and pointing gesturing, which we added later. And so here's kind of interesting scenario. And this is a distributed NSF center at UC Berkeley for seismic research. And so NSF funds a center that has very large structures that are shaken, simulating earthquakes. And obviously it's very expensive. You can't have too many of these around the country. And a lot of the researchers that in this project are actually remote from Berkeley, and so they need to collaborate with the local researchers. And so they were a good customer for this technology. And you can see, you could see hopefully some value in doing this. The robot can sort of ask about specific parts of the structure. The pointer was actually quite useful. And yeah, they can actually resolve some questions that would be pretty hard to do otherwise. So they're it's a fairly naturalistic design, pretty similar to telerobots that came later. We also ran them a number of times around Telegraph Avenue, which is Berkeley's kind of cultural center. Extremely diverse place, and one of the few places where a telerobot doesn't actually stand out that much. You're a little bit different, but everybody around you is strange people, and yeah. Anyway, so it's a nice environment. There was a lot of good engagement in Telegraph. One thing I should say is also it's a personal robot. It's kind of the antithesis of a utilitarian robot, especially with the pointer, because the pointer is there not so much to do anything useful, but it's actually there to tell human beings to do something for you. So it really inverts the usual notions of a useful robot. Okay, so now on to the UPM, which we did shortly after. And as Ken mentioned already, we were working for a while on risk robotics, which was really reacting to what we saw in industry, which is people were really not using programmable robots very much. Hard automation was completely dominant, and stuff wasn't getting programmed. So we thought maybe a better way to approach it is to I suppose, in a more principled way, design minimal hardware that would get used for automation. And so one exploration we did was called the UPM, which was a what's the simplest possible planar manipulator. And basically, it's a plate. It's a rigid plate, and it moves only in the plane. But it can move any number of objects into an arbitrary configuration. So if you haven't seen it, it's a fun and simple technique. Basically, if you have a planar plate, you apply, let's say, a rotational field. You'll see the velocity field looks like this. And velocity is closed under addition, which is another way to say a rigid composition of rigid motions, superposition of rigid motions is a rigid motion. So, all right, that's good. But what happens when you apply friction? Well, the velocity fields go from being basically additive. Because of the nonlinearity of friction, you get not additive fields. And so two frictional fields, force fields with different centers give you actually something new, which has more degrees of freedom than the original. So that means you can keep adding motions, do them in series, or you have to do them in series, and you'll get more and more complex force fields, which you could then perhaps try to invert to do inverse kinematics to control objects. That's not very practical, but there's another trick, which is instead focusing the fields. So if you think of the blue curve as being the velocity over time, you can see it's got an asymmetric positive and negative cycle. The areas are the same, but the time spent positive and negative is different. Because the friction force depends only on the sign, there's more force in the positive direction where it's spending more time. So that's the red curve. So basically, this asymmetric motion in one dimension will feed objects in one direction. So if you basically take that blue linear feeding field and then superimpose a symmetric rotational field on it, the further you get from the center of the rotational field, the larger the rotational velocity is. And that field is symmetric, so it tends to basically cancel out the effects of the linear field. So the net force field looks like this, basically a strong concentration of force at a center, and then it decays to the outside. So we built several prototypes to try this out. The first thing you do is you grab stuff from the kitchen, wherever you can find it. It's a baking dish and some voice coils. And it does feed objects in 1D, but it doesn't do much else. And we started, sort of went through many iterations, went from baking dishes to countertops, then added these voice coils, which Dan has some really cool photos of. This is kind of, I guess, robot engineer porn, nice big, beefy, multi-G voice coils. And then eventually we got some aircraft. That's honeycomb, aluminum, titanium aircraft airliner floor, which is very stiff, light, and rigid. And everything else we actually went back to plastic in order to reduce the amount of sort of spurious vibration in the system. And so it basically works. So this is a sorting task. So the task is to move the blue chips to the left and the red chips to the right. And it succeeds after a while. And what's the dirty laundry? Yeah, all of these are sped up, by the way. It's not actually that fast. We have quite a bit of dirty laundry in this project. Well, you see some of it. Anyway, it works. All right, and then this one's actually playing chess. These were by an undergrad we had, Neil Aldrin. And it's a little bit hard to see, but it does, and it takes some time because the pieces are packed fairly tightly, but it does actually execute a series of moves from a chess end game. And at some point, somebody wins, but we got to keep moving. So, and the last one, is that moving? Yeah, it is. So we have a camera. We have a camera over the device. So Neil did another demo, very useful, which is basically as soon as a hand appears in the workspace, the beer can moves towards it. So this is just the first iteration of this. We obviously, since then, have become more concerned about exercise and health, and so we have a version that moves it the other way, moves it away from the... Okay, so, yeah, well, anyway, so one of the lessons from the work, especially on props, was that actually human-robot interaction and human-human interaction was really interesting. So I switched directions at that point. Let's see, we've got about... When should I finish, Ken? Because how much questions?
We can take another 5 minutes or so.
Okay. I was going to do a bit more than that, but so, because it goes till 4:30, so how much questions is there?
So yeah, take 10.
All right. So, okay, so, all right, so video conferencing. So there's the Mona Lisa effect, which probably all of you are perceiving right now, which is it looks like the painting's looking at you. That's a problem for video conferencing, for group video conferencing, because when you have a room full of people, you actually can't have gaze. You can't look at somebody, because wherever you either look at everybody or nobody. Everybody shares the same perspective. It's actually very hard to fix. It's widely misunderstood effect, even by people that have built these systems commercially. You actually can't fix it at all with different camera layout or different screen layout. It's fundamental to basically the behavior of the display. So, and make it a bit more, perhaps more direct. Right now we have a video screen, a normal video screen with a bunch of people looking at the actor number 2 on the other side. And we're also seeing what number 2 sees. And as we move forward, now we're looking from number 1's position. And you can see the screen's foreshortened a little bit, but you're still perceiving a frontal view. And if we go to the other side, again, you see the foreshortening, but the perception's not changing. So basically, yeah, there's no gaze through video screens. So that's a bit of a problem. So you can fix it. You have to build an autostereographic display. How do you do that? Autostereographic means spatialized, viewer-dependent view. So this is back in sort of 2005. You can do it if you're Samsung and you can actually build displays. We wanted to build one in the lab. So you can actually do that. The normal screen diffuses light in every direction, but our goal is actually different with this project. We actually use retroreflection. So now if we have that yellow projector there, our goal is to get the image from that projector instead just to go to that person. That way the next person can have their own view that faithfully corresponds to a different camera position on the other side. And probably details I can't go into, but retroreflection, there's a few different ways to do it, with lenticular screens. The other thing we need to do is, in the other dimension though, diffuse vertically so that the viewer still sees something even though their head's in a different place from the projector. So we did also N iterations of that, which I won't go into. They included hairspray and a whole lot of other tricks. But we got a pretty good display in the end. And I think you can get the idea. There's 3 people sitting here. Each one has a projector that's going to project their own view, and that's all they'll see. And the images of the people on the screen have a camera sitting over them. That will give them the correct view on the other side of the system. So you can fully reproduce spatialized video. And instead of what you saw before, with everybody getting the same view, this is a view of the screen. This time, everybody's looking at the person on the left. So from their view, they see eye contact. But the person in the middle sees people looking to the left, and the person on the right sees people looking further to the left. So it does faithfully reproduce the display. It's reasonably inexpensive. And it does matter. So I can't go into full experiments, but we did some well-studied trust experiments, and actually several different experiments on also deception. And basically, when you do fixed gaze, you by and large reduce the deficit between actual face-to-face collaboration and video conferencing. If you don't do it, you have a that's quite a significant difference. It's like a 30% difference. It's very large anyway. And this is reproduced in a number of experiments. Okay. So Ken mentioned the language learning work that we did. This is really all initiated by my former student, Matt Cam, who's now at Google. And the idea is to basically, well, try to bridge the demographic language gap that's very prevalent in India, but also in a lot of other colonial developing countries where basically the colonial language ends up being the language of the middle and upper classes. For those people that are not fluent in English, there's almost a brick wall separating them from access to even decent schools and certainly to universities, etc. And there's some other challenges that are hard to appreciate if you're used to a Western culture. The teacher attendance rates in a lot of the rural schools is less than 50%. So that you have a less than even chance of finding a teacher even if you can make it to school. So anyway, we developed some games designed to teach English, got some nice results. yeah, so they appeared in several conferences. We actually did get some measured improvements in learning, and especially nice improvements in retention of students. Basically, they really enjoyed using the tool. So these are very simple, basically adaptations of familiar games like Frogger and some shooting games with some well-founded early language skills, such as letter-sound correspondence and word recognition. So you layer those into a standard game, since we're not really innovating in the game design. But this is the second last study we did, where we have at the end, Matt did a longitudinal study, which has results that are a little bit stronger than this, but to first order, it works. The project went for quite a while. Matt's still doing related work, although less work in India now. Okay, so a question that's suggested is, can we go a lot further? Can we go beyond sort of very rudimentary language skills? And can we also help children learn about more about the world? And although this project was focused on India, there's a similar literacy gap in developed countries, in the US in particular, between the top quartile and bottom quartile socioeconomically. There's nearly a 3-to-1 vocabulary gap before children go to school. And basically, there's students, but basically there are many families that don't engage their kids verbally, that don't read to them. That gap, once established, tends to be regenerated in school, and those kids stay behind. So we wanted to explore more rich interaction and also more situated interaction in the long run. So roughly inspired by a young lady's illustrated primer, which is the subtitle of Neil Stephenson's Diamond Age. But if you've read that book, you remember the primer was actually this very interesting, powerful learning tool, actually backed by a human, but it was always there. Kids could always sort of interact with it, ask questions, and learn something. All right, so we implemented a somewhat richer game, which is a 20 questions game. So there the dog actually hides something in a box and then asks the child to guess what object it is. And the child then has to do a lot of reasoning, have some qualitative understanding of the world, and be able to compose appropriate questions. And as I mentioned up there, this was done with Machinima, which is a very interesting technique. It's basically taking God games like The Sims and controlling the characters, really directing the characters inside the game, using their emotion controls, telling them where to go, etc. And it's a very cheap way to leverage all of the artwork that the game designers did to your own advantage, almost like having free actors. And so anyway, so we got the right behaviors from Spot. It plays the game. We scripted the entire game, but nevertheless, and we were able to do a study with an experimental preschool near Berkeley, and we got generally very good results, especially if you compare the agent to the human. So the kids solved a number of the challenges. They didn't need too many hints. They asked a lot of questions. And generally speaking, the red curve is the agent condition. Generally speaking, the agent was more successful. So the dog was more successful than an actual human playing this game, adult human. And when we actually asked the kids, would you prefer to play the game with a human or with Spot, what do you think they said? Spot. So yeah, this is very revelatory, I think. As at least AI researchers, we spend a lot of time agonizing and worrying about passing the Turing test. The lesson here is, who cares? People prefer dogs anyway, not just children. But if you're going to interact with agents, there's actually this very interesting big design space. Talking human agents tend to disappoint. Talking dogs really don't. So Spot was surprisingly fun and effective with limited behavior and content. But that and also the experiences with Millie got us really thinking, what if we could do a deep learning that would really understand the speech, that had some compiled set of facts around the world that could synthesize and do much more of the reasoning automatically and digest appropriate text to expand its content database and perhaps even learn more fun behaviors, more open-ended fun behaviors. And I've just taught a course in deep learning at Berkeley, and I have a lot of better idea of what we could have done, and it's really quite daunting, or encouraging, though. One last thing in this space, we did an experiment on persuasion that has a little bit of the same character. This was sort of, to give a very short explanation, this was oriented towards healthcare and behavior change. And the experiment was to test how well can you influence somebody given them some information about healthcare. And we found that dialogic interaction, that is interaction that mimics real human-to-human interaction, was much more persuasive than non-dialogic forms. And we did it using a human. The utterances, there were voice utterances that were triggered. We pre-scripted them so it wasn't too much like a human-human interaction, so that it could plausibly be done fully by machine. But it was Wizard of Oz, meaning that a human decided which thing to say from a short script. But anyway, again, with deep learning, we could have done this probably very effectively with full automation, and again, much more open-ended. So anyway, so the high-order lesson from all of that work was that there's sort of a momentum shift from perhaps the early 90s in terms of human-computer interaction, when back then it made a lot of sense that computers mostly functioned as useful tools, and you wanted to keep gratuitous paper clips really out of your face as much as possible, giving you advice. And now things are really quite different. You really are much more delegating tasks like managing your inbox or driving your vehicle to a pretty intelligent agent that you need to express high-level goals with. So that sort of influenced my progression back into more AI research. I guess this actually started before I really made it a research priority. I think when I was doing HCI, I was still really missing actually working on AI, so I ended up consulting a lot on the side, something like half-time. A lot of it was actual part-time leave. And mostly on kind of big data problems, ad targeting, personalization, etc. Most recently, though, at Google, it's really just deep learning research. So having done that work for a while and also having worked on other software, in the earlier projects, I have a real affinity or desire for better tools. I feel like there's a sort of ideal set of tools that we don't have right now, and they do matter if you're trying to rapidly explore and try things out in machine learning or deep learning. The faster you can try things, get them debugged, and get some results, the more ideas you can try. And the tools can sometimes be the limit on that. So what we've been doing recently is trying to sort of optimize, I suppose, figure out what is the design space, what decisions are forced on you, and what do you have freedom on. And the desiderata for future tools include things like basically having full natural GPU support, which means not having to do special commands to use a GPU. It should be just math, similar to MATLAB. Should be able to say A times B, not worry about where that's happening. You should be getting full performance out of your CPU and network, not 0.1%, as in, unfortunately, Python. But also, you shouldn't have to worry if you do want to distribute across a platform, across many platforms. You shouldn't have to think too much about how to do that. You should be able to write for one machine and then have the distribution taken care of. There has been some really nice innovation in programming languages recently, so let me just keep going. At the same time, you don't want to throw away all the code that's been written. And remarkably, there is an optimum solution, we think, even that resolves those two conflicts, which is using the Scala language, which is actually a different front end to Java, and is capable of running all the Java code in the world. We heard about this earlier, actually, another project using Scala. So most of this comes from Scala. We've also written the libraries necessary to make inference on CPU and GPU seamless. Anyway, the language itself, though, gives us a wonderful set of affordances. The toolkit's basically two parts, the matrix part, which is roughly the NumPy, SciPy part, and BIDMACH is the machine learning part, which implements both standard machine learning and now deep network layers. And it also has another component currently called BIDMAT Spark, which started out life as enabling the code to run on Spark, but now actually also runs standalone and has a more general distributed semantics than Spark. And comes pretty close to the goals that I mentioned on the previous slide. It's particularly nice for reinforcement learning where you can't necessarily build a learning system that uses off-the-shelf deep network layers, but there's some other operations, some marginalization, sometimes multiple regressions with several different, both the ultimate reinforcement reward maximization, but also regression of value functions, etc. Basically, it's very nice for that. You can define custom layers as well on the fly and have them run at full speed. So here's the set of classes. We have these algorithms implemented. It compares very well with other tools. Because it's fully rooflined, we, from the beginning, designed to maximize performance on CPUs and GPUs. It actually outperforms many distributed systems even without being distributed. But when distributed, it even offers some orders of magnitude more improvement. All right, so I think I'm almost there. So current work, we're working on scalable and fault-tolerant machine learning, top slide, which is about, well, I can't really explain it, but basically trying to do distributed operations, basically have that ability to distribute single machine code seamlessly that I mentioned before. We're also working on interpretable machine learning, which means, especially for applications like self-driving vehicles, trying to help users understand how the system made its decisions. And in the current implementation, we're using basically highlighting hotspots, highlighting the system's attention as a way to describe to the user what's happening. So basically, the vehicle's road following using clues that are roughly along that side rail. It also periodically looks up in the sky for whatever reason. We don't really understand that. Maybe looking for the sun to tell which way it's going. I'm not sure. But it seems to regularly do that. Anyway, that's a visual explanation. We're trying to also build a causal layer on top of that, which basically masks out some of these potential cues to see which ones are real cues. And lastly, we have a kind of open-ended project looking at reframing deep network training, which is right now a kind of a hodgepodge of different techniques that are drawn from optimization theory and applied to a domain to which they, by definition, don't apply to non-convex optimization. We're proposing instead to use Monte Carlo framing, which does exactly fit the kind of problem that deep learning is attempting, or training is attempting to solve. And this is already yielding a bunch of interesting results, but hopefully will give us some mileage in the future. All right, so let me wrap up. OK, so let's see, summarizing the evolution. So I started out detecting canny edges, and then most recently moved. The work we're doing now, we can actually detect the edge for real. Basically, with a convolutional network, you can really reliably detect the edge. And you can even discriminate the edge from canny. I checked this, and it works. So I suppose the higher lesson is that we've really come a long distance where we used to have to sort of hand featureize perception pipelines, do a lot more stuff manually. I think this is a very exciting time. I think this is one of those peaks in innovation that happens every few decades, probably, where a lot of the things that are being done now actually will probably be very long-lived in terms of their influence in future. So yeah, so I'm excited to be sort of getting back into robotics right now. And yeah, well, anyway, thanks again for the attention, and I guess I'll take questions.
Thank you, John. Really appreciate it. We do have time for one or two quick questions. Anyone? Okay, oh yes, here we go. Mark. No, sorry. Russ, I'm sorry.
No good. I'm almost embarrassed to ask after the way you finished, but in the middle you talked about the polynomial kinematics and all this beautiful work in algebraic geometry and things like that. And that sort of died on a vine just because the complexity of those formulations was so high, and people don't use it a lot today in favor of other sampling-based type stuff. So, but is there a future where the computation comes back and makes those valid again? I mean, are those? Do you see a future in that, or is?
So how many people have actually tried it? So it has implemented a roadmap algorithm using the algebraic methods. Who's actually tried it? You have. How bad was it? Oh, you as a grad student? Oh, yeah, but it was a lot, yeah, but we figured out a lot of stuff after that. No, I mean, well, look, I'm not going to make a case that it's the best thing to do, but no, I mean, I think we stopped doing it, which is a big factor, or I stopped doing it in my group. Other people did something else. And, you know, again, we did implement it a bunch of times. It worked fine. It wasn't that complex. I think it's really perhaps more of a cultural phenomenon. Again, Dinesh is the only one that actually tried it. I don't know if you told everybody it was intractable, but I don't think anybody else has direct knowledge, right? It's one of those things. You see the constants. They're worst-case constants. You don't have to enumerate whatever it is, points. The actual critical points in typical environments were, and also the other results came after you anyway. But no, we implemented it a bunch of times. I think probably the biggest thing was that there weren't like nice off-the-shelf tools for doing the algebra that were very efficient. We built some of them, but we didn't distribute them enough. And that was a barrier. If you look at what the real algebraic geometry people is, because they like that stuff, they've done it, basically. They've implemented many generations. I didn't list all the stuff, but there's dozens of works, actually, mostly theoretical, admittedly, but trying to improve the algebraic complexity of the roadmap algorithm. And more recently, there was the numerical work that I just flashed up there, which is actually working at 4 or 5 dimensions using sort of numerical techniques.
But
so,
I mean, even inverse kinematics. I mean, like Charles Wampler's continued to fight this battle and find zeros of polynomials with, you know, for incredibly complex systems and things like this. But these are not somehow the go-to tools. And I didn't mean to say it about your work in particular. I'm just saying like somehow all this beautiful math about you know, polynomial kinematics. Is that coming back, do you think? Do you think, you know, fast computers means that stuff becomes valid again? Well,
I think you should use the best methods, but you know, sometimes it takes a bit of work to find the best methods. There's definitely, you know, research is a dynamical system. It kind of has a momentum term and an energy term. And the momentum is pretty strong. And if you do something different from the mainstream, you need a certain amount you need to keep doing it a certain amount of time to get anybody to try it. And I think we moved around a lot, and we probably didn't spend enough time perhaps distributing code, because it's very different from what other people were doing. We were sort of also ourselves split between different communities. So I don't think there's really anything fundamental, but I think you have to look problem by problem. Like I say, we can solve some pretty massive, gnarly, big systems, probably orders of magnitude bigger than people are used to solving. For whatever reason, it's published. I think there's some code that Yannis wrote, just hasn't really been taken up.
There's also research has a big noise term as well, and randomization terms. Actually, which is a perfect lead-in to the next session, where we're going to talk about open problems. So, John, there's so many things we can talk to you about, and I think we'll have a chance during the banquet tonight. We'll be all hanging out over many drinks. So please join me in thanking John for coming out.